Reciprocal leveling is another method of enhancing leveling accuracy. During ordinary precise leveling, we always keep the distance between the instrument and the backside point, and the instrument and the foresight point, we keep them equal. Why do we do that? Because this will eliminate instrumental errors and also will counteract the curvature and refraction effects. Now, these two effects will be the same in the foresight direction and the backside directions, and at the end they will cancel each other. Now, although we put the instrument in the middle, but still we have to limit the backside and foresight distances to 50 meters or less, and that will minimize the effect of climatic change. But what about the scenario where we cannot put the instrument in the middle? Take this example where we are crossing a river, we are crossing a body of, let's say, another conditions that we cannot pass through. Then what do we do in this case? We do use reciprocal leveling. So reciprocal leveling, it's a method to go over, let's say, or to deal with the situations where we cannot put the instrument in the middle. We will show you here two cases. One case is when we do two independent setups. Case one, two independent setups. What do we mean by that? We just take the instrument when it is close to the first point. We take a back. Of course, this is the benchmark. As we learned in surveying, always we take a backside at the benchmark. So we take the backside. Point B is the point being unknown elevation. So we take at the first measurement the instrument as near to the benchmark, which is point A, let's say, and then we will take a backside on the benchmark and take a foresight at the unknown point. Now we will take the instrument, take it to the other side, or we will put just another instrument on the other side, and this is what we call simultaneous leveling, which means we have an instrument here, instrument to take the measurements at the same time almost, because we don't want to wait until the atmospheric conditions to change, and the measurements will not be as expected. So the first one is that we put the instrument at point near the first point, take a backside at the benchmark, and then take a foresight, and then calculate the elevation of point B. And we can call it elevation of point B1. Then we move the instrument, as we said, then take a backside. We move the instrument to next to point B, and then again we will take a backside at the benchmark. This is the second independent measurement. So we take the backside at the benchmark and then the foresight at the unknown point, and then again we will calculate the elevation of benchmark of the unknown point B the second time, and then we'll take these two measurements and average them. So this is the first method. The second method is a little bit different is that we want to do a loop. We want to do a closed loop from starting from A as a backside, and then calculate the foresight on point B and calculate its elevation, and then continue from point B by assuming, or let's say making point B as a turning point. And then we will put the instrument again at the second point, continue. We will not go backside on the benchmark. No, we will continue from the turning point B and close on the benchmark. In this case, we will calculate another elevation for the benchmark point, and hence we will have two values. One, which will be the given elevation of the benchmark, and the computed elevation of the benchmark when we complete the loop. At this point, we have two values, BMA at the beginning, which is given, and the calculated. The difference is what we called in the surveying course, we called it the misclosure, and they will take this misclosure and we will distribute it by the means of, we will recalculate the elevation of point B. Now, or give it a correction. We'll take the misclosure and apply it to point B, and then point B after this correction will be the final value. So let's see the equations. Now, here in the case, first case, as we said, it is as simple as taking the instrument at the first position, take backside RA and the foresight RB, as we know from surveying. So this is the reading at the instrument is at A, station A, near to the first point, and then we take backside and foresight. How do we calculate the height of the instrument? It's by adding the given elevation of the benchmark A, and we add to it the reading of the backside, which is RA. And this is the height of the instrument. How do we calculate the elevation of point B here? Is by, which is the unknown point, is by taking the foresight and subtracting it from the height of the instrument. The foresight reading is RB. So at the end, the first case, which is EB1, the elevation of point B from the first setup near point A will be the elevation of the benchmark, the given one, minus or plus the RA, which is the backside, minus the foresight. Now we will take the instrument to near point B, and we'll do the same thing, but the same thing, we are taking a backside at the benchmark. So this one will be R prime A, backside on the benchmark, and then foresight on the unknown point. But this time the instrument is close to point B. So the height of the instrument, again, it is the elevation of the benchmark given plus the backside, which we call here R prime A. Then elevation of the point B. In the second case, EB2, B2 means in the second case, it is the height of the instrument minus the foresight, and this will equal to height of the instrument minus the R prime B, the one that we measured at B when we are in the second case. Putting the equations together, the elevation of benchmark 2 equals elevation of benchmark A plus RA prime minus RB prime. In this case, we have now two values of the elevation of point B, one from setup number 1 and one from setup number 2. The first setup at near to point A, which is the benchmark, and the second setup near to point B, which is the unknown point. So we average these two values. We take elevation point 1 plus 2 divided by 2. And if we want to replace elevation of B1 by its equation here, and the elevation of point B2 from the second case from its equation, we just put them here and we come up with the difference elevation between these 2 points as this, and at the end we will have the elevation of point B equal elevation benchmark plus the delta elevation between A and B, which can be calculated from this equation. As simple as that. Now, if we have, this is a numerical example, it is just direct substitution in the previous equation. But what do we have? Let's see, what do we have? So as we said, at setup number 1, when we have the instrument near to the station A, which is the benchmark, we have the given elevation of the benchmark, we assumed it as 100 meters, and then reading at A, backside, and then the foresight at point B, the difference, and calculate elevation of benchmark 1. Then go to station number B, take the instrument near station B. The same thing, we have the benchmark as at 100 meters. Take the backside on the benchmark, the far point now. And this 1.3, take it to the near point, which is B, the unknown point. Then again, RA prime, R prime A minus R prime B. And this will be minus something. We add, as we saw from the equations, we add the elevation of benchmark to the difference. And this will give me elevation of benchmark 2. So we have now one elevation and another elevation from the first setup and the second independent setup. They do not share any information in the measurements. And then we take these values. As you can see, they are different. So we take their average, and this is the final elevation of point B. Let's see the second case where we will do a dependent loop. Like we start a loop from the benchmark and we'll go to B, and once we take here a backside and then a foresight, And then we'll take the instrument from near A to near B. And again, we will deal with B as a turning point. Turning point, we'll take a backside. Now at the turning point, not the benchmark like in the previous case. And then we will find, we'll read also for site 2. We finish the readings now for the calculations. How do we do that? The first setup, when we are at the benchmark, the reading is RA, the reading is RB, and then the height of the instrument of setup number 1, which is here, the height of the instrument above the datum, and this is the HI1, height of instrument 1, setup number 1 here. So the height of the instrument equals the elevation of the benchmark A plus the backside, and which is, we have it here as RA. Then how do we calculate the elevation of point B from this setup here? This is the elevation of B, and this is equal to the height of the instrument minus the foresight reading. So we take it, which is RB, and at the end, elevation of benchmark 1, point B, the elevation of point B in the first setup, it is elevation of benchmark A plus the difference between the backside and the foresight. And now we come to the second setup. In the second setup, here is the second setup. It will be between the point B and back to the benchmark. And in this case, we take a backside when the instrument was near B, and the reading is R prime B, and we'll take at the benchmark, we'll take R prime A. The same thing in the setup, we'll take a backside. We add it to the elevation of point B we just calculated in the previous setup, and this where we will have the height of the instrument 2. We take the height of the instrument after we calculate it, adding the backside to the elevation of the point, and then we'll take the foresight at the benchmark, and we calculate a computed, we call it the computed value of the benchmark A, because we return to it closing the loop. So this is the computed elevation of the benchmark A. How do we do it? By taking the height of the instrument and subtracting RA from that, which is the foresight reading and the benchmark. And if you just put the values here, elevation of benchmark A, which is the computed value, equals the difference in the backside and the foresight in the previous setup, and add to it the backside and the foresight. You see here, it is the foresight. RA is the backside, and here is the foresight. Then from the second setup, this is the measurement at B, which is again the backside. So here it's the backside from the first setup, and this is the foresight. And then RB prime, when we are reading at point B, this is again a backside, and this one is a foresight. One from the first setup and the second setup. At the end, we will put all these values here, and this is the elevation of the benchmark computed. So we have the original value of the benchmark that was given, and we have the computed value after we closed the loop. Now we can calculate the difference between the computed elevation of the benchmark and the given. This will be called the misclosure, and then the misclosure is this is the equation for the computed elevation, and we have the original elevation of the benchmark, which is the elevation of benchmark A. So here we put the equation from here, and we subtract from it the elevation of benchmark given. And after we just put the numbers together, we have elevation of benchmark, we will cancel out, and the misclosure will be these values. These are measurements from the first setup, and these are measurements from the second setup. How do we distribute this the corrections? It is by taking each point, and then we want to see from which setup it was measured and how many setups do we have. So point B, it was measured from the first setup. What is the total number of setups? It is 2 setups. So we'll take for point B measured from the first setup divided by the number of total setups. We multiply it by of course, not the misclosure, negative of the misclosure, because the misclosure is something we want to remove. So remove it by multiplying it by a negative. Then we add this. This is the share of point B, elevation of point B, share of correction, and we add it to the elevation of point B that we calculated from setup number 1. As you can see here, the correction of AB equals 1/2 multiplied by half of the misclosure, and this is the value. We take it and we add it to the elevation of point B that we calculated from here. So elevation of point B from the previous equation, and elevation of point B, it is as we said, it's from here, and then we put it and we put the correction, and that's it. This is the final elevation benchmark. Let's go for a numerical example and see. So this is a numerical example. As we said, as when we were at the station number 1, setup number 1, the elevation of the point is 100. These are the readings, and then the height of the instrument, adding the elevation of the benchmark plus the reading, and then we will calculate the elevation of point B, which we will use in the second setup as a turning point. Now we go to the second. This is the elevation of point B1. We want to continue now, so we're going to use the elevation of point B as a turning point, and we take a backside from there, and this is the backside and the foresight at the benchmark. And how do we calculate the height of the instrument in setup number 2? By adding the backside, this one, to this point, to this elevation, which is the elevation of the turning point. We get the HI2. How do we calculate now the computed elevation of the benchmark? By taking the height of the instrument 2 minus the foresight from setup number 2. Then we calculate the misclosure. And the misclosure in this case, it is this value that we found for which we computed for the benchmark, minus the original value of the benchmark, which is 100, and this will give you minus 0.22. What is the share of point B? As we said, it is 1/2 because point B was calculated from the first setup out of 2 total setups, and there is a negative sign of the misclosure, so it is minus 1/2. It's 0.11 multiplied by a negative sign, so the share of point B is 0.11 meters. So what is the final elevation of point B? It is the calculated elevation here from setup number 1, and you add to it 0.11. Once you calculate it, this is the final elevation of point B, and this is exactly the same elevation that we found when we did the procedure as in case number 1. So for now, this is the reciprocal leveling.